Okay, welcome to the DeltaQSD tutorial, designing systems with predictable performance at high load. So what we want to do is we want to show you an approach for helping you design and predict the performance and feasibility of systems even before building them. Let me first explain how the tutorial is going to be organized. This is a full day tutorial. We have 4 lessons, and the first 3 lessons will have small lab sessions. We have a software tool that lets you compute interactively the CDF of the performance of the system. The first lesson, we're going to present case studies. I'm going to present 2 case studies from the company P and Sol, which are real industrial case studies. And then lesson 2, we'll talk about basic compositional systems. This is systems where you connect components and the components do not interact in any nonlinear ways. And we'll show how to build with that. And then on lesson 3, we will add coupling. Usually in most real systems, the base is compositional, but there is always going to be some coupling giving nonlinear behavior. And in the final lesson 4, we're going to talk about overload. So this is what happens when you stress a system beyond what it's designed to do. And we'll talk about temporary and permanent overload, but we'll also give a real world design example of our approach for the Cardano-Shelley blockchain crypto algorithm. So the first 3 lessons will be done together with small lab sessions. So the idea is to have a half-hour lab session near the end, and we will show our interactive tool running on a Jupyter notebook, and all the participants can log in to our Jupyter server, which is running in Belgium, and we'll be able to interactively compute system performance. That will be doing for the first 3 lab sessions. Okay. Okay, introduction. So first I want to get a little bit of context, what the whole approach is about, what kind of systems that we're targeting. We're typically targeting large systems with many independent users where performance and reliability are very important, okay? For example, systems that have large flows of independent data items subjected to unexpected overload systems. So typically things like cryptocurrency platforms, but also large-scale communications networks, telephony, mobile telephony, publish, subscribe, social networks, client-server, large client-server systems used in internet commerce, distributed sensor networks. So large systems with lots of users and data flowing. And the approach that we're going to present is called DeltaQSD, DeltaQ System Design. And this was developed over 30 years by a small group of people around a company called Predictable Network Solutions Limited. So we have a few of the brains of P and Sol here, if you want to talk to them. So this approach has been widely validated in large industrial projects, and there have been basically some publications on this, but this tutorial is basically really the first time that we try to bring everything together in a coherent way and present this as a system design approach. So DeltaQSD is what basically this compositional approach where you can combine components together that are basically independent of each other. It's a stochastic approach. We will use stochastic notions like cumulative distribution functions, probability density functions for predicting and computing the performance and latency. And you can also do that for partially defined systems. So this approach is intended to be used during the design process. So even before you even know the complete design, you can already start computing what the predicted performance is. Okay. So what are the goals of this tutorial? Well, we want to present the 2 main concepts underlying DeltaQSD, which we call quality attenuation, or DeltaQ. So this will be shown as a form of CDF of latency, but it's a general concept where perfection is not attained and there is something lost. And the second concept is called outcome diagram. So this is basically a causal graph of the relationship between the different things that a system is doing. And we will give you some practical experience with our software tool. So you can actually get intuition on how we can use this approach and how you can actually think about systems before building them. Okay, so we will construct systems as independent parts. We will add coupling to that. We look at refining partially defined systems. So the idea is that you don't know everything from the beginning. You only know pieces, and you build as you design the system, but you already want to compute performance and feasibility before. Okay, so a few words about P&SOL. So P&SOL, Predictable Network Solutions, is at the origin of DeltaQSD. So it's a UK company which is specializing in design and diagnosis of large-scale distributed systems, especially as regarding their performance and feasibility. It was founded in the early 2000s by people from the University of Bristol. So it comes out of academia, and it has been involved in many, many industrial systems, British Telephone, Vodacom, Boeing Space and Defense, and so on, IOG, IOHK, cryptocurrency company. And so what I'm presenting you today has a long, long history. Okay, so before presenting the case studies, I want to talk about the two main concepts. So these are the concepts that will be kind of like the thread throughout the whole tutorial today. This is quality attenuation and outcome diagram. So these concepts are not so complicated, but they have a lot of consequences. So you will gradually get to understand really the usefulness as we present things today. So quality attenuation, you can kind of consider it as latency and failure together as a first-class entity. It's a cumulative distribution function which combines latency and failure. Okay, so that's very abstract, but I will show you it. It will become very practical in just a few seconds. The second concept, outcome diagram, is basically looking at the system behavior. So if your system has to do something, send a message, get a reply, display something, do some computation, that is a system behavior seen from the outside. So an outcome is a well-defined behavior, okay, that has observable start and ending, and it has a latency and failure probability, which is a delta Q attached to it. So the outcome diagram is basically combining that for the whole system. So it's a causal graph, a directed graph that combines all of the different outcomes of the system. And so you can compute the delta Q, the latency failure of the whole system by combining the delta Qs of the different components, okay? And also it works for partially defined systems, as we'll see. Okay, so let me introduce, before we get into the case studies, some of the basic points. So in general, I'm going to have these blue-green boxes when I talk about system block diagrams, and the more yellow-orange diagrams will be outcome diagrams, and the one will be corresponding to the other. So if we have a component C here on the top left, it has a delta Q, which is a latency and failure probability. So on the right, you can see a cumulative distribution function. So you have the delay here of this between the input and the output message. And here you have, for a certain percentage of messages, have a delay less than or equal to D. And there is also a failure probability. Maybe this thing is an improper random variable. And then the outcome diagram on the bottom. So here we have a block diagram of two components that are just connected together, very simple system. But the outcome diagram has two outcomes. So the first outcome is C1 doing its thing, and the second outcome is C2 doing its thing. And these are causally connected. The stop event of outcome 1 is the start event of outcome 2, okay? So a little bit more detail on each of them. So assume I have a system component, like a database here. I have a query entering and a response coming out. So the response takes some time. This time is not a constant, okay? This time will vary for many different reasons. It can vary simply because the computation takes over time, but it can also vary because the input load, the number of queries per second, when you increase it, causes the component to overload, and that may also cause the time to increase. So on the right, you see this delta Q as cumulative distribution function, okay, which basically tells me the probability that the delay will be less than or equal to d. And it's actually not a true cumulative distribution function. It's actually what's called an improper random variable, because it doesn't actually end at 1, but it may end at some number less than 1, which means that there's been a failure, okay? In that case, there's some probability that the component will not give an outcome. So the delta Q represents both delay and failure in a single concept, okay? Okay? And so when you're designing a system, you have its actual behavior, which is the red delta Q, the observed delay, but you also have a system requirement. You're designing the system to have some particular demands on it, and that is also a delta Q. Here I show it as a step function here, as a stair-step function, and then you can compare the two. So basically the red delta Q, if you want the system to satisfy its requirement, has to be to the top and to the left of the required delta Q. Now, the red one can fluctuate. If you overload the system, then everything will slow down and the red one will move to the right. Now, if the two curves intersect, which is not a good thing, that's called a hazard. So that's a probability of the component not meeting the requirement. So if there's some intersection, there's some probability that it doesn't meet the requirement. So making this intersection is called arming the hazard, okay? So this is how you can actually use this approach also for risk management, okay? So I'll say a little bit more about outcome diagrams too. So assume now that you have two components, a front end, FE database DB. So you have a user request and then it's forwarded Q to the database and you have a response. So you actually have two components doing computations. You have two outcomes. The OFE and ODB, but you have a resulting outcome, okay, which is of the whole system. So this is a very simple outcome diagram. We'll see much more complicated ones where you have two outcomes causally connected, and the total delay, delta Q of the system, is the sum of the delays of the two components. But this, so we write it like this with this special symbol for a sum. So this is not actually a sum of numbers. This is a sum of two cumulative distribution functions. So this sum is actually more complex than just a simple arithmetic sum. It's an operation called a convolution. And doing this convolution operation gives you a lot of information about the whole system, depending on the two component parts. Okay, so that's just a starting point. And now we go to the case studies. Okay, so in the case studies, we're going to be diagnosing a misbehaving system. So these are industrial case studies where some huge company had a system and it wasn't behaving right. So they brought in P and Sol to diagnose, basically to be like Sherlock Holmes, figure out what's going wrong and fix it, okay? But there's of course another way to use delta Q is to design systems, which is actually better than diagnosing misbehaving systems. But these systems were actual industrial systems. Let me show two case studies now. So there's what I call the small cells case study and iPhone launch case studies. So these are actual industrial case studies. They have been somewhat anonymized since they're covered by NDA. And in both of the case studies, we're diagnosing a misbehaving system. We're trying to figure out why it's misbehaving. But later on in the tutorial, we'll show how to design a system. So the Cardano Shelley, which is a cryptocurrency platform, there are some algorithms in there that were actually designed by P and Sol to get to obtain particular performance requirements. So that will actually show you a more reasonable approach for ΔQSD. Okay, so it's better to design than diagnose. Prevention is always better than cure, but in the current state of affairs, it seems that a lot of diagnosis is necessary for real systems. Okay, so let's go to the first case study, small cells. So let me first tell a little story. So there's an MNO, a mobile network operator, who shall remain unnamed. So this is an actual one. I will not tell them the name of it unless we have a beer and it's not recorded, okay? So you have small cells, which are low-powered cellular radio access nodes with a small range, and then there's a backhaul using consumer DSL. This was for mobile telephony, and the system was built, but it didn't scale. So if I remember correctly, it worked up to a few hundred users, and then it started giving very bad things, in service interruptions and so on. So this was, of course, panic mode for the company. So they brought in P&Sol. So P&Sol diagnosed this using, so they basically devised first the outcome diagram for the complete system, the delta Qs for each part. They put in observation points to measure that, to pinpoint the problem. And in that way, they were able to diagnose and fix the problem. So I'm going to show you that. So here is the block diagram of the system. So you have on the left, so I hope you can see it, you have left the user here at point A, you have a small cell, a CP control point, you have the control point connecting to a wholesale access network, then you have the ICPE control point, then you have the national interconnect, and then the MNO core. So basically, you're stepping towards the MNO core from A to E, and then to the reference point E, and then you go back in the opposite direction to connect to the other user. Okay, so all of these parts are not directly owned by the MNO, by this big company. So they had to basically lease or make contract with the different companies for the different parts of this. And there were, of course, requirements. So all these connection points, so B, C1, C2, and D, were ruled by certain requirements on the performance, okay? So the MNO believed that its contracts would actually be sufficient and the service would be delivered and the hazards would not be too dangerous and that there wouldn't be any residual hazards. So this was an error, and we'll see why it was an error. Okay, so P&Sol first gathered the evidence. So they, on the user point A, they added a synthetic traffic generator and they put observation points all the way to E, okay? And then they add internal observers to get more precise measurements, so the BCD. So the outgoing diagram is actually not so complicated. You have the causal connection going from A, B, C1, C2, D, E, and then back D, C2, C1, B to A to the other user. And for each of these little arrows, you can measure the delay and failure probability, the quality attenuation, okay? So these are, with all these points, you actually get a lot of spatial fidelity, and this was enough for diagnosing the system, okay? Okay, so let's now talk about how the system is behaving, some of the results. So here we have some observed delay against the experiment runtime. So horizontally, we have here the runtime from 0 to 140 seconds. We have delay, okay? So each of these little points is a packet in the system. So this, of course, gives you a lot of information. And this was the delay for the round trips from A to E, and then back from E to A again. We can split this into upstream delay and downstream delay. So the upstream delay goes from A to E, and the downstream goes back from E to A, okay? You can see that the upstream has a lot of variability, in fact, 5 times greater than the downstream, and the downstream is much less variable, more constant, okay? Notice that if you take a slice here, a vertical slice at a particular time, and you look at all the packets in a particular window here, you can determine a delta Q, donc a CDF of the delay of the packet, okay? So you look at this upstream, you think, oh, this upstream is very bad. So you might think the problem is in the upstream, but actually it's not the upstream. So let's go look a little bit farther here. So we have now, let's look at BCD paths and DCB, upstream and downstream, okay? And the delta Q is not stationary, so it's changing according to the run. And at some points, it has a strong anomalous behavior. So we're going to zoom in on that. So here, for example, so the upstream behavior, you can see there are some outliers, but they're not big. But in the downstream behavior, we have some very big outliers where the delay is much increased. So focusing on the downstream, so this is downstream, D to C and C to B. So here, D to C, so the national interconnect is doing fine here. But here, C to B, we have a problem. Okay, at some point, we have a very large peak here. So let's zoom in on that. So here we zoom in on that. So this is the C to B. So you see from the whole delta Q, we zoom in on the part that has the problem, okay? So on the horizontal axis, we see the experimental runtime. You can see there's some fluctuations, but at 595 seconds, there is a very quick increase in the time, and it's slow, and the decrease comes very slowly after. So this is like a whole second where basically the system is, the performance is interrupted. So this actually is a typical delta Q overload behavior. If you have a queue in the system or you have an input buffer and packets are coming in, if the packets come in too quickly, that buffer gets full, and emptying the buffer is very slow because each packet in the buffer takes a certain time to treat it, okay? So it's very easy to get into trouble very quickly, but you get out of it much more slowly. So the point is that temporary overload, which happens, what happens here, has a long-lasting effect, okay? So this is what gave the performance problem, okay? So later on in the tutorial, we'll talk about temporary overload to understand this more in detail. But for now, we can see here that the buffer is filling quickly and emptying slowly. So this is a typical component behavior that you can zoom in using ΔQSD. Okay, so with this, we can actually measure, this is the measured delay on the left. We can actually make a mathematical model of the system, and you can see that they correspond closely. Okay, so if with this, we can actually now start diagnosing the problem. So there's a queue forming in the wholesale access network. So the arrival rate from the MNO security boundary is exceeding the server's capacity of the XDSL line. So this causes a temporary overloading behavior, but this temporary behavior, which happens very quickly, has a long-lasting effect, okay? So this is in breach of the contract, which does not allow for such a long degradation, okay? So this delays all the traffic going through the system, including the control traffic for the small cells. And the small cells, they don't like this kind of thing. If the control loop is too long, they will fail, okay? So the figures are actually way beyond 5 times that limit. So the small cells were also failing because of this, okay? Okay, so a delay of this magnitude affects the voice quality, okay? The small cells are breathing, so they're stopping inappropriately. And of course, the business case is incredibly weakened from this. Okay, for curing the system. So the point is there's an unmanaged hazard, and it's sitting with the MNO, the connection between the MNO and the wholesale, the contract. The two systems, the MNO's core network and wholesale access network, are not composing. The prerequisites of one are not being met by what's the post behavior of the other, okay? Now, the problem is that the MNO, they match bandwidths, okay? Sure, the wholesale access net is able to accept the sufficient bandwidth of packets, but that's not enough, okay, batching bandwidth, because the delays have a lot of variation, okay? They should have matched delta Q. So this is called a quantitative timeliness agreement, okay? So then PNSolve made a recommendation to the MNO, and this was put in the corporate risk register and technical training, et cetera, so that the MNO would not have this problem in the future. Now, your mileage may vary whether they've actually implemented these recommendations. But this was able to fix the problem. Okay, so that's the first case study, small cells. Second case study is a similar one, but here the delta Q exposed a tip of the iceberg, exposed a huge number of problems in the system. So this was an iPhone launch. So there was an MNO in the UK who was was initially supported by just one, okay, the iPhone. A second MNO wanted to also launch support for the iPhone. And it was kind of common knowledge that their performance was very bad. And the first MNO was very happy. And they had prepared a major ad campaign, okay? So, of course, the second MNO was brought in again, P and Sol, to diagnose the problem. And P and Sol was correctly able to diagnose it and correct the problem. And the result was that the second MNO actually had a better performance than the first one. And it was the first one who was embarrassed. Okay, so that's the little anecdote. Okay, so here's the structure of the system. So on the right, we have the mobile terminals. We have the transmission backhaul network, the radio network controller, the MNO core, and the internet. Okay, so we put in observation points. So again, we look at end-to-end delta Q and we diagnose and to pinpoint the problem, okay? So here we look at the round trip time. Here it's over the first 100 seconds, okay? Now this is fake data, It has the same structure as the real data, but for reasons of NDA, it's not the actual data. So here we observed a round trip delay. Seems to be fine, right? Over the first 100 seconds. Okay, let's now look at the full duration. So now we have 800 seconds. Now notice what happens here. Around 450, we have a service break. We have excessive delays happening here in this ellipse. So this is directly correlated to bad experience for the end user. Okay, so we have to study this. So we compare now the uplink and the downlink. Okay, so here we have now 3 colors. Okay, so the red one is the uplink, the blue one is the downlink, and the green one is the center part from the radio network controller back to the internet to the other radio network controller. Okay, so if you look at what's happening here, so typically companies will focus on the downlink. But you can see that in the downlink behavior here, it's actually fairly uniform. There's only one outlier here, okay? The round trip in the internet, the green part, there's no issues. The MNO suspected the downlink was the problem, but as actually you can see here, it's the red, the uplink was really where the problem occurs, okay? So again, we found this problem in the uplink. But in this particular case study, this was really the tip of the iceberg. There was a lot of problems. Once P and Sol started digging into the problems, they found one problem after the other, okay? So there was a slow PDP authentication, okay? The authentication servers, HLR servers, were highly loaded. So this was improving this. Also, here it is an improvement. So the random access network was not configured right, okay? There were 2 restrictive content filters, okay? And then there was more problems, okay? Particular equipment interactions in the TCP download. So they increased the throughput by 47%. And already the MNO was now looking at as number 1. And finally, fragmentation of the user data into different parts, okay? So improving this gave also an additional 100% improvement. So after correcting all of these problems, so you see how it works, you diagnose, and you focus in, and you start finding problems. In this particular case study, a lot of problems were found. In the first case study, it was really only one major problem. Okay. Okay, so that's the second case study. And now I want to talk about, I want to give a lab. First lab. So what we're going to do in the tutorial is we have made a software tool. So we would like everybody, so you normally you need to have an SSH figured on your system. No, we can stop the recording at this point. Okay. Thank you. Okay, the second lesson will be about compositional systems. So this is the heart of ΔQSD, is putting together systems from independent parts. So this is the first step. This is kind of the heart of it. In lesson 3, we're going to add couplings between the parts. And in lesson 4, we're going to talk about overload and the need for multiple levels. Okay. But today, right now, we're going to talk about independent parts. And most systems do largely consist of independent parts. And so we're going to talk about quality attenuation and system design with it and outcome diagrams. And I give you a lot of example systems. Okay, so quality attenuation. So we have already seen it in the first lesson. It's a cumulative distribution function. A message comes in, a message goes out. There's a latency, there's a chance of failure. And then there's the time that's not constant. So there's a jitter. It's a function that has many possible delays. So all of that is combined into a single quantity, which is the delta Q. Okay. So a very important point is the fact that we're combining delay and failure into a single quantity. And very often they're considered completely separately. Delay and then failure handling is another thing. But in fact, it's very important, it's very nice to have them together into a single quantity because there's very often trade-offs between them, okay? For example, you can reduce failure by increasing delay. One way is to simply change the tolerance, the requirement, or in other ways by retrying, for example, okay? And when you have several delta Qs, when things are changing, you sometimes want to compare them. So this is actually comparing delta Qs is a basic operation that we're going to need when we start building systems that require certain properties. And so you want to, here we have two delta Qs, delta Q1, delta Q2, and you want one of them to be completely left and above the other one. Then you can say here delta Q1 is strictly less than delta Q2. And it can be strictly greater. And if they intersect, it's actually not order. So this is a partial order. And another basic operation of delta Qs is what I call adding two delta Qs. If you have two components that you connect together sequentially, so the message coming out of component A goes into component B, and component A has a delta Q shown on the top of the diagram here, and B has another delta Q in the bottom. Then the overall system has a delta Q, the red one, delta QAB. So the question is, what is this one? So this is a really basic operation, and this operation is called convolution. So let me give you the intuition. So because convolution is actually a really important operation in real systems. So here we have an example. So here's the delta QA. Okay, and it's a cumulative distribution function. We will look at the probability density. So that's the derivative of this. So it's very high when the probability is increasing very fast, okay? So that means there's more chance the delay having a high probability density. So both A and B have particular probability density functions. And now we can compute the probability density function of the overall system AB. So the overall system will have a delay T, a total delay. And this delay, if there's a packet coming through, will have a delay in component A and B. So those delay, it's split into two parts, which I can call little delta and T minus little delta. So the overall delay is T. So the little t is a particular little delta plus T minus delta. So you can see here in the diagram, if the overall delay is T, there can be a delay little delta in A and T minus little delta in B. And the overall probability density of AB will be the product of the two, because we have two independent events. The two systems are independent, so the probability density is the product. And then, so now I wave my hands vigorously and I say we will sum over all the values of little delta to find the total probability density for the value t. And this sum, of course, is an integral because we're looking at little bars of width d little delta. So that gives us the total probability density is the integral of PDF A delta PDF B t minus delta from 0 to t. So this is a convolution, and this is what you get when a final outcome, when there's many different ways of getting there. You basically add up all the different ways. So in the ΔQSD approach, the operation of convolution is a very basic operation that we're going to use very often when we connect systems together. Okay, so that's enough mathematics. Now I want to start doing some design. I want to start very simple designing with just the delta Q. So we're not looking at outcome diagrams yet. A simple system that is just a connection of two components. And I'm going to show you two different designs, a top-down and a bottom-up design. And we will also look at feasibility. Maybe we want to build a system and it can't work. There's some fundamental problem because it would require some delay, for example, to be negative. Okay, this is something we can determine using ΔQSD. So let's do this, and I'm going to do it kind of in a back of the envelope way for this talk. I'm going to use a very simple delta Q, which is a uniform distribution. Okay, so it has a constant density between minimum and a maximum. This actually is a reasonable approximation for real components. But of course, many other more complicated delta Qs occur in practice, okay? And we're going to add and subtract these uniform distributions. So remember, the addition operation is convolution, okay? So some introduction to the uniform. So a uniform distribution is an approximation of a component with a buffer and a server. So it has little a here is the minimum time in the component, and little a plus s, which is the spread, is the maximum time in the component, and the density here is constant in between. So this is the one we're going to use because we're going to do all of our computations here on the back of the envelope, okay? Of course, a real software tool like the Jupyter tool that we're using can do much more complicated delta Qs, but it's really good for the intuition to do some back of the envelope computation, okay? So the first thing I want to show you is convolution of uniform distributions. So here we have two uniform distributions, A and B. The A has a little spread from little a to big A. B has a spread from little b to big B. So we can characterize each of these distributions with two parameters. And now we have a distribution C, which is the convolution. So it's like you're connecting component A and B to make component C. Now, it turns out a fairly good approximation is that we assume C is again uniform, so that the convolution of two uniforms is a uniform. So this is not exactly true, but in the case of just two uniforms, the error is quite small. And you can see that the spread, the minimum value for C is little a plus little b plus a little bit more, okay, because of the fact that we have a distribution that is not constant. And we can see the maximum value, big C, is actually big A plus big B, but a little bit less. And the spread is actually the maximum of the two, but a little bit wider. So the little m here is the minimum of the two spreads, okay? So it's like you're combining the two in a naive way, but things are a little bit worse, okay? So that's a good way of thinking about the convolution of two uniforms. And now let's go into some examples. Let me first do a very simple example. So I'm doing a bottom-up design. So bottom-up design is very simple. I have two components, A and B. They have known delta Qs, delta QA and delta QB, and I want to compute the delta Q of my system. So bottom up, I have my components, I'm building up to a full system. So in order to make it simple, we're going to assume uniform distributions for A and B, and we add them to get C. So we can see that the delta Q C, the minimum is the minimum A plus B plus a little bit more. The spread is the maximum of the spreads plus a little bit more, okay? So the overall delay is a bit more than the sum. The overall the spread is a bit wider. So things are a little bit worse than if you would be just adding naively the two uniform distributions, okay? So here's a numerical example of that. So here we have a first component, which goes from 5 to 10 millisecond delay, a second component from 5 to 10 milliseconds, which is here. So the little m is equal to 5, the minimum. So if we compute the result, we can see that the C, the minimum of the combination is A plus B plus M over 4, which is 11.25. And the spread is the max plus M over 2, which is 7.5. So notice it's not going from 10 to 20. It's going from a little bit more than 10 to a little bit less than 20. And the spread is not 5, but it's 7.5, okay? So this actually is a pretty good approximation, okay? That's our first design, bottom-up design, okay? So to get you warmed up into it. Now let's do a more interesting example, a top-down design. So in this design, we know the overall required performance of our system, delta QC in black here, and we know component B. Component B is given component. And then we have to say, what kind of component A? So we're actually putting constraints on the component A, okay? So we can do that. So we assume we know delta QC and delta QB, and we're computing the delta QA. So this is actually a deconvolution, but we're going to use our equations that we did and use them in the opposite direction. So this will tell us that A, the little a, so the minimum delay of the first one is C minus B, but actually minus M of 4. It has to be a little bit better than C minus B. Otherwise, it doesn't work, okay? And the spread here, you can see it depends. If the S, it's a more complicated to compute because you have different possibilities because you're using min and max. So if you assume S, the spread of A has to be less than the spread of B, then it has to be less or equal than 2 times the SC minus SB. Okay, so what does that give in a numerical example? So here I have a given component, which goes from 7.5 to 15 milliseconds. And the component B has a delay from 5 to 10. So naively, you could say, well, A has to go from 2.5 to 5, okay? But in fact, it has to be a little bit better than that. It has to have a delay of 1.25 and going to 6.25, okay? But be careful. This is the way we look at this. Let me first explain here. This is actually a requirement on the new component here. So that means the delay of A is maximum 1.25, okay? So this is a requirement on the component. And so we can see that A has to be quite good here in order to make this design work, because B and C are actually very close to each other, okay? So that's a back of the envelope computation. Now we can do an infeasibility check. We can see that the A, it's still possible in this case, but if B and C would have been a little bit closer, it may have been impossible. And that's something we can know without actually building the system. So we can actually compute the conditions on B and C. And so if these conditions are held, no component A is possible. So we can compute this. We'll compute this using our approximation for uniform distribution. So the C is A plus B plus a little bit more, and that the spread is the maximum plus the minimum divided by 2. So in order to solve these, so we have to see what is the condition on A. So we'll compute for A and SA. So there's actually two cases because we have max and minimum. If SA less than or equal to SB, then we know that SA, we can compute it this way, is 2 times SC minus B. Of course, the spread has to be greater than 0. Otherwise, the component is not possible. This gives me a condition. And the other one, the minimum delay of A, C minus B minus this, also has to be greater than 0. The delay has to be greater than 0. And this gives me another condition. And if the SA would have been greater than SB, then the max minimum give other solutions. So we have more conditions. So this gives us a Boolean condition. So it's basically if the first one and the second one are infeasible, that means if either of these two first conditions is not satisfied, then component A is not possible here or here, and both of these have to be impossible. So this gives us a condition on feasibility. So this is not a simple condition, huh? And this is a computation for our approximation. In the real tool, you're going to be doing deconvolution, okay? So the tool can be very precise on when a system is feasible or infeasible. So this is really making your intuition very, very precise, okay? So this introduces the notion of subtracting distributions. So when you go top down, it's very often that you have to do a deconvolution. So you have to find the distribution which, when convolved with a given distribution, gives another one. That's actually mathematically quite hard to do. For specific distributions, it's easy. But for a software tool also, it's not a problem, okay? I mean, it's a lot of computation, but the tool can do that, okay? So this is actually clearly a case where if you have a software tool that actually gives you a lot of power to reason about feasibility, okay? And there's a final point, is the goodness. So when you do bottom up, you're computing the known behavior of the system, okay? But in the top down, you're actually computing a requirement. This component, which makes it, has to be the worst case of the components, okay? So this, you have to be careful about how you interpret it, okay? Now, a final point, so this is design. You can also diagnose with ΔQ. So in order to be complete, this actually corresponds again to the small cells case study, okay? If you have a pipeline of components, so a lot of components connected together, similar to the small cells case study, and the overall ΔQ has a problem, okay? It's bad in some sense. So then you can basically do a kind of binary search. You can pinpoint the problem and find out which component is doing badly. So this is the approach that was used in the small cells, okay? Okay, so this is the first part of what I want to talk about. This is the designing and diagnosing with ΔQ. Now we get into the real meat of the approach where we're looking at outcome diagrams and designing with outcome diagrams. Now we're going to combine components, not just connecting them sequentially, but combine them into full systems with non-trivial systems behavior, okay? So in order to do this, you have to be very careful about what is an outcome diagram, okay? So you're looking at the system from the outside, you're looking at the behavior of the system, you're not looking at how the system is constructed. So outcome diagrams are very different, for example, from UML diagrams or state diagrams. UML diagrams talk about what's inside the system, but outcome diagrams, they say nothing of the internal states, okay? That you're looking at only the system from the outside. And that is a very, very useful way. It's not so much done so far in system design, but as we will see, it's a really useful way of looking at systems. And you can bring all kinds of components together in this way: software, humans, mechanical devices, they can all be represented in outcome diagrams, okay? And we can do performance and feasibility computation very early on. Okay, so now I have to really explain clearly what it is, an outcome diagram, and it will take some time for this to sink in. So I will start by a very simple example. I have a single component, a server or database. I have a query and a response. So an outcome is a behavior of the system. So what is that? Well, a behavior system is defined as a pair of a start event and an end event. So an event is an occurrence of something that happens in the system at a particular time and place. So a query and a response. And this corresponds here to this outcome, query and response, okay? And an outcome has a delta Q associated to it. So a quality attenuation in general, but a CDF in our timeliness model, okay? So this is a causal connection. So this is looking at the system from the outside. So as we'll see, as we start to build more complicated systems, the outcome diagrams don't resemble at all the block diagrams of the system. So here we have a single outcome and a single component, okay? If we now go to the next, so if we now have two components, we have two behaviors. So the first component, you have an input message and an output message. And the second component has an input and an output. So the output of C1 is the input of C2. So there's a causal connection between those two outcomes, okay? So outcome one is causally preceding outcome two. So you can combine them in a directed graph and have a bigger outcome, which is U1, R1 here with its own delta Q, which is the outcome of the whole system, okay? So in general, this is going to be a directed graph with causal connections, okay? And a final point, a little bit more subtle point, is outcome diagrams is actually more like the classes than objects, okay? Here we have a click, for example, and a query. So the behavior is the query comes after the click. So whenever we have a click, any event U will give an event Q, okay? So that this outcome is corresponding to a class of possible event pairs, okay? So when event U and event Q both occur. So the little squares here are the events and the circle corresponds to the outcomes, okay? So whenever there's an actual packet coming into the system, for example, that's an event, and a packet leaving would be another event. So if you have many packets, then you would have many instances of that outcome. Okay, so now let's use this for system design. Now I'm going to show you a bunch of system design examples, okay? First example, very simple, client server. So here's a client server, a more sophisticated one than just a single component. So here we have a user sitting in front of a browser. We have the server, for example, Amazon, somewhere in a data center, and the network is in between the two.
Sorry, Peter, would you like to maybe clarify that these are two different diagrams overlaid? Or one of them, the middle one is a block diagram, the one that
okay. So the blue diagrams is the system block diagram. So these are actual system components, and things happen. So in the lines are actually connectors between the components. Whereas the yellow diagram, which I here overlay, is a directed graph showing only causal relationships between abstract things, which are called outcomes. So when I click here, a message goes to the server and a response comes back. So the outcome diagram, you can show it like this. I click user click. So internal to the browser, a query is created. The browser will send the query over the network. The query will be received at the server. The server computes a response and sends the response. The response is sent over the network and received at the browser. So these are all events, huh? And then the browser processes the response and then the response is displayed, okay? So each of these is an outcome. Each of them has a delay, delta Q. Okay. So that's a very simple example. You can see that the block diagram corresponds to this causal graph. Okay, now let's start introducing examples where you have more subtle kinds of system behavior. So the next example I'm going to introduce is a cache memory example. So here we have a cache in the left side of the diagram. So we have a cache and a main memory. So when we do a read, the read goes to the cache. If the cache has the word, it immediately returns. If it does not, then there's a miss and it goes to the main memory and then comes back again. This means that the cache has two possible behaviors. It can either succeed, which is called a hit, or it cannot have the memory word, which is called a miss. And there we will, in our outcome diagrams, to show these two possibilities, we introduce an operator here, which is called probabilistic choice. So when we have a read event here, there's two, when it goes into the cache, there are two possibilities. Either the word is in the cache or it's not. And if it's in the cache, which is called a hit, then we have a hit outcome here, and we immediately return. If it's not in the cache, we have a miss outcome, and then we do a main memory read. So the cache, the mem here, which is basically the memory read operation as seen from the processor, can be refined into the cache behavior, which uses this probabilistic choice operator. So we're using it as a prefix operator because here there is some decision being made which of these two outcomes will be realized, okay, in the probabilistic choice. And the return, so the result of the hit or the main memory will be the stop events for both sides. So the delta Q of the mem operation can be computed from the delta Qs. So I'm not going to give you right away the semantics, but you can actually mathematically compute that. It's actually a weighted sum where H and M are the hit and miss ratios. Delta Q hit is the time that it takes for the cache to determine the hit. Delta Q miss is the time it takes to determine a miss. And delta Q main is the time of a memory read. So that if there's a miss, we do a main memory read. So here we have a convolution between the miss and the main memory. And the hit and the miss sides are computed with a weighted sum, okay? So delta Q itself is a function of delay. So here we're doing a computation. This new function, delta QM, is a computation of the three given primitive delta Qs, okay? So you can see with this, we can actually compute the cache behavior. So here's a numeric example. So let's say that the hit takes one time unit here. So this gives us a step function. So after one time unit, we have 100% success. Let's say the miss takes 1.5, so a little bit longer. So we get a 1.5 here, and the main memory read maybe can take 4, for example. So if we combine these three computed distribution functions using the equation I just showed you, this gives you this gives us this function here, where we, after one time unit, we have a 95% chance of success. And then after 5.5 units, we have a 100% chance. So this is the overall delta Q of the cache memory, okay? So this is an example using probabilistic choice. This typically we can show cache. Okay, let me show now another example. This is a timeout. Timeout is a very important operation in real systems to handle things that take too long. So here, again, we have a block diagram, and we have our outcome diagram underneath. So here we have a send, okay, and it goes to the cloud, which is whatever it's going to, and a response is coming. So something can happen inside here that I'm not worried about what it is exactly. All I know is that when there's a send, sometime later, a response comes back, okay? Now, this response might take a lot of time, so we're gonna do a timeout. That means when we do a send, we're gonna start a timer, and this timer, after a given time, will have a timeout event. And whichever of these two events, the timeout and the response happens first, is what the return is, okay? So this is modeled using an operator called first to finish. So this is written as follows, a prefix operator using an existential symbol here. So here again, we have a start event, and then we have two things happening in parallel. And the first one that stops is considered to be the stop event of the overall outcome, okay? Again, you can compute the delta Q of this combined operation as a delta Q's, combining the two delta Q's, C and T here, and it gives us this equation. So it's the sum of the two delta Q's, but minus the product. So where does this one come from? Well, this is actually, and you can compute this using the semantics. It's not too hard, but Hossein will say it in a minute. You're basically using the semantics of first to finish. So if the first one means it's not the case that there are zero events, and if you compute it using that way, you can see where this kind of strange formula comes from. Okay, but if we use this using delta QC and delta QT, so the timeout is a step function. So after the timeout threshold, it stops, okay? And if you combine the two, you will see that before the timeout time, we have the normal response of the cloud, but after the timeout time, we have an immediate success because it has been a timeout, okay? So this success means that there is a result message, but of course, has not been a successful read. It means only that we have successfully had a stop event here. So this is the delta Q of a timeout, okay? Okay, so we're not done yet. We're gonna give some more examples. So we already showed a few operators, sequential composition for combining components that are done one after the other. We have a probabilistic choice when you have a choice between alternatives, and first to finish synchronization. And this one's also called any to finish. But in fact, we need one more operator to have a set that is actually complete enough to model many different kinds of systems, which is called all to finish. And to show the all to finish, I'm going to show another example, which is parallel work, okay? So here, parallel work, basically, we have some tasks that we want to do, and it's a lot of computation, but we want to do it in two separate pieces, which could be done on separate processors. So we split the task into two pieces, and there's two workers that are going to do it. And so the two workers will have their own delta Qs, T1 and T2. And the full task is complete when both of them are finished. So when the first one and the second one are finished. And we denote this as an outcome diagram with a for all symbol and our two outcomes that are executing in parallel. And the overall delta Q is now the product of the two. So for example, if T1 takes a little bit of time, it's uniform. T2 takes more time, it's also uniform. Then the full one will of course take the time of the slowest one, okay? And semantically, you can show that it has to be the product of the two delta Qs, okay?
Probably, so we had, just to make sure that there is no confusion, that cross sign that you're showing, this is not vector.
This is arithmetic multiplication of two functions. So for each, so the delta Qs are a function of delay. And so for each value of the delay, the value of the overall delta Q is the arithmetic product of the delta Qs of the components. Yeah. Okay. Okay. Now we can actually start doing more complicated examples. So here's a more complicated one, which I will not handle, but Hossein is going to handle in a moment. Here's a bigger system, just as an example. Here we have a network memory read with a local cache and a timeout. So here on my side of the network, I have a cache. If I have a hit, I have the value immediately. If there's a miss, it goes to the memory, and the memory is on the other side of a network here with mread, mreturn. and there's also a timeout because the main memory read might fail. So this can be denoted, modeled with this outcome diagram. So the first probabilistic choice is models the cache. Here, the first to finish here models the timeout. And here I've put in a second probabilistic choice, which models the possible failure of the main memory read. So one of the nice things about the ΔQSD is that you could model failure probabilities. So I want to show, this example shows that. So even very small failure probabilities. So assuming the main memory has an error correcting code here, and there's a 10 to the minus 116 chance that it fails, okay, this error correcting code, check. And so we can add a probabilistic choice here to model the fact that the main memory read might fail, okay? And it doesn't matter that this value is very small. We can actually, when we compute the overall delta Q, we can actually compute what is the effect of this 10 minus to the 16 on the overall read, where you have the timeout and the cache. How does this ECC fail affect this? So this is something we're going to show later, okay?
But is there any sense of one part leading to success, another part failures? Or do I indicate that on this slide? Because sometimes you want to return and say everything was fine, okay, and sometimes you want to return and say, actually, no, we didn't do anything useful.
So in the diagrams of structure, in the tool, you can actually say, you can ask, right? So you can actually, there's sort of a process of introspection where you can your things, so then you can quantify. Okay. So say the idea of putting it into the tool, it actually turns out in the debate, effectively created a embedded basis.
Okay, yeah.
The other thing is that, as I'm going to show, you can do two things. You can either change the outcome diagram to explicitly have an outcome, which is the failure.
Yeah. That's
Or,
what I was
or
thinking.
which is the hit. So,
Yeah,
sorry,
yeah.
which is the miss.
Yeah.
Right. Or you can do something else, which is that you can do properization that I won't show in the slides, but I would be more than happy to talk to you. But
So the idea is that you can do algebraic transformations. So we've defined an algebra. So
yes.
Hossein, we've defined an algebraic Hossein's work of this with certain kinds of rules that are possible. The same way that electronics engineers use Kirchhoff's laws and so on, we have actually defined certain kinds of transformations you can do in these diagrams. And what you can do is this failure, which is sitting inside here, this ECC fail, sitting down deep inside, you can transform it to bring it to the top, okay? And then, the probability is going to change as it's being transformed. And we have actually an example of that in the paper we submitted, that you can actually then directly see what is the global failure probability. So this is what I'm showing is really only scratching the surface. There's a lot of mathematics behind this. So all of this, what I'm showing, there's a formal algebra has been defined for this. And you could do equivalence transformations, keeping equivalent timeliness. Okay. Okay, let me just now in lesson 2, give a more general kind of presentation of how you would do system design using this approach. So now I'm talking a little bit more abstractly. Yeah. So I want to design a system now, and it has some particular behavior, an input and an output events. Okay, and we design it step by step. So we make refinements. Certain components are known. For example, we know that there has to be a request and a reply. And maybe we know the delta Qs of those requests and reply, okay? So we know that that's part of the system, okay? But if we add that in, if we make a refinement step, then there's still a part that's unknown. So we keep refining the system until we get our final design. And at each step, like in the middle here, we can estimate what the performance and feasibility is. So this is kind of like the top-down example. We can say, is it still possible? Is this design still feasible? So it might be that this gray, as yet unknown subsystem might have an impossible delta Q, okay? We're asking too much. It might need a negative delay. And that means that our design has reached a dead end and we have to rethink our part of our design, okay? And eventually we come up then with our completely defined system. But in the intermediate steps, we can actually already do a lot of computation. So the top-down example is showing that. So here's kind of how it works. It's a top-down approach. So here, assume that we know the delta Q of the overall system, we know the delta Q of the request, we know the delta Q of the reply, but we have this unknown subsystem that we have not yet designed here, okay? We can compute the constraints on this red delta Q unknown. And if it's infeasible, then we know that we have done something wrong. We're expecting a negative delay somewhere in our telephony system. Then we have to go back and maybe redo the request or reply parts. Or maybe that's not enough. Maybe there is an inherent problem in the overall system requirement that has to be changed because no systems are possible. So the idea is that you're fine, and if you reach a dead end, you have to basically backtrack and rethink part of the system and go another direction. So in general, it kind of looks like this. So this tree with the blue knobs is actually how you design, is exploring the design space. And the root of this tree is a totally unknown system, and each step down to a subtree is a design decision. So here, for example, I'm saying I'm using a particular database, Cassandra, or I'm using Amazon Web Service or whatever. And this is going down and eventually get to a completely designed system. So if I start, for example, by going to the left here, D1 and DX here, I may, at this point, this is an internal node. So this is a partially defined system, but I may already be able to determine that it's not possible to design it. The delay of a component has to be negative. So I don't even have to go down to the fully defined systems. Already, halfway through, I can figure out whether the design is feasible or not, okay? So this whole tree is a tree of partially defined systems, starting from an unknown system and going to a fully defined system. So the idea of ΔQSD is that I can really very quickly prune this and determine infeasibility early on. Okay.
Can I jump in with an anecdote here?
Absolutely.
You might think that negative delay isn't ever asked. Right? And no piece of stupid. I have a friend at Beat. One day he found stuff and yet he said, "You'll never believe the other." I turned up, they wanted to do cloud. And they said, can you deliver packets across the UK network in -30 days? So basically, they have got themselves into a position in their design in order to fulfill their cloud alien activity requirements. They needed the network. And the thought this was wow. Now, the second thing is, if you were to do this for things like a lot of augmented reality and immersive systems, the metaverse stuff, right? You also find out this basically requires they build the system and then they start to look at them, put them in the real world, and they find out that basically they I actually was on a train one day. This happens to me a lot. I was talking to a guy who was coming back from having talked to somebody about the networks. And I said, don't you have this problem? He says, yes, we have that problem. Basically, but the system is really possible. Right? But he said, we've got lots of money out of a certain company for doing this at this point. And then that particular company pivoted away from metaverse and it started to realize its possibility. I can tell you about 21CN and how people change their documents and change their history so that they look like they're successful as they discover infeasibility, whereas they could have done it before.
Of course, you can do the minus 30 seconds if you compare a millisecond or they open up the rest of their system too. This means you have to cover that time from someone else.
Well then now we're designing
Right.
for
And
this.
you realise that there is a dead branch to go one or two steps above and then you change.
See, this is what you have to do.
Yeah.
first, huh?
You can do the design. This is a formalism that gives you that negotiation power.
So yes, you know, it turns out, guys, you've got to find 30. Actually, guys, I can't do the UK network is a minimum dynamic of this milliseconds. You've got to turn around and find this back, and then you find you can't. Right? So suddenly you've worked out that your multi-billion things you were hoping was going to be worth billions won't succeed, and things like distributed haptics, like in a way, feel touch or the rest of it, that is impossible because I've been informed human beings detect they're really sensitive to knowing when things should be touched. Because this, as monkeys jumping from branch to branch, you need to know the branch that way. What you evolve is to the fact that if it's a millisecond jitter compared to your mental body, it's yes.
Instead of feeling like a solid surface, it feels like a sticky stuff.
Or it feels like it might be the you lose cognitive absorption and therefore immersion is lost. Okay. So this stuff comes, you can relate all of this stuff in certain circumstances back to things that people really care about in order to make systems.
Beautiful innovation space. Innovation space.
Yes. So the whole point about the high-tech industry is you're trying to walk the line between what's desirable and what's feasible. Right? This gives you a way of figuring out what's feasible, or in particular what's infeasible. Now the whole agile methodology is supposed to do this, right? But fails to deal with the issues of things being infeasible, and particularly infeasible at scale. A lot of problems arise because actually you can build your distributed haptic environment perfectly well where everything's in the same building.
Or in the same book.
Or in the same room. That works great, right? But when you say, oh, well, actually, now this guy's supposed to be California, then it will work. But if you don't have a model that can incorporate all of the attenuations, right, and tell you what the result is going to be, you don't find that out until you spend too much.
Yeah. So the infeasibility has to be first class in your model, not something that you find out later. You represent it explicitly in this model. You can compute
So
it explicitly.
This is a kind of rational way to approach designing.
Managers don't like that, huh?
No, managers don't like it. Everybody wants to believe that their thing will succeed, and they want to hang on to that belief as long as possible. Actually, what this will do is destroy their belief that the thing will work at the earliest possible moment.
We have a year,
Which is the best place to destroy it. Instead of at the end.
That's the right way to do it.
Yeah.
So do you overlay business decisions?
Oh yes.
Yeah.
So
So
this should be part of the methodology you can use in the business decision, right? And when you pivot your startup because you found that the thing you originally thought was feasible, that's the right time to do it. Before you spend a lot of money on one product.
So that is actually a good way. That's not a failure. I mean, failure is good in a sense, huh? If you find it early on. Failing early is very good.
This is designed to help you fail as early as possible.
Or detect failure.
In the
detective,
phrase failure you fail often, which is what some startups do. They've got failing early. This is the fail early method. So what we
Using this method, succeeding in whatever they're trying to do, then become how good at estimating.
Well, actually, okay. So what happens if you? Okay, I have a nickname which is Neil Davis Destroyer of Dreams. Right? Because basically, people breed these systems and I destroy them. But I'm also a creator of realities. Right? So what happens is, people come to you and say, guys, how is it going to work, right? So you can say, do you change the aspiration of your system? Do you change the requirements? Do you change that? So that's when the experience and engineering judgment starts to come in, because you can say, oh, wait a minute, maybe we could do this way, or we could do this. Oh, we can only do this if the cache is this big, right? Now you're starting to, but you're going away from gut feelings into
something calculable.
something calculable.
And you could also say things like, actually, maybe it doesn't need to respond. Maybe 100 milliseconds is good enough. Okay, hours of it. Okay. Right. So you could explore this trade-off between what your top-level requirement was and the feasibility of your refinement process.
Yeah. And often, refining that top-level requirement is actually the real value of this process, right? Because we've been in a situation, you won't mention where the engineers thought they had to do something in 50 milliseconds. The real customer thought only 50 minutes, right? And information we lost between the customer and the actual system. So we were trying to build something that was impossible, but actually it was possible because the requirement was not really lost, because it was as fast as possible. One of them thought that meant 15 minutes, and one of them meant 20 minutes, right? So we get out of this as fast as possible.
So actually, to some extent, a lot of the value of the whole approach is that thing right at the very top, between two yellow squares and the grey circle. Right? If you can get people to define what's the delta Q they want for their outcome, actually, that generally represents about 80% of the value of the approach. Because people very often they just say, "Oh, I want to be as fast as possible." They don't even think about what good enough is, and that actually, if you don't have a specification for what's good enough, the engineering problem is solved already. Leave it to start with. Nobody will tell you what's good enough. So if you you
force people to tell you.
design the system to an unspecified requirement. So actually getting that specification in at the beginning is the thing which turns distributed system design into actually.
What Peter says. So another thing that I learned from these guys is that if you want to force someone to change their mind, you have to give rigorous argumentation. You can't just say, it's not going to work loudly, but this gives you actually a rigorous argument. It cannot work for this and this and this reason. And a somewhat reasonable manager will then change their minds, okay? So you have to come with rigorous arguments. And this system approach lets you make those arguments. Okay, so yeah.
It gives you a language to talk about. Correct. Just drawing that picture of a kind of CDF in a couple of steps provides a way of saying this is what I want, right? Or for an engineer to ask the question, is this good enough? Right? You just that as providing a way to interface between hopes and aspirations and reality and design, and that's in too many cases completely missing.
So that's what we're trying to do, to make a meta thing here. So this tutorial is part of an ongoing, it's a snapshot. We want to take this knowledge, which P and Sol has developed, and which you can see, there's a lot of useful stuff there, but which is not really so well known, into something concrete, documents, tools, tutorials, so that people can start using it. Okay, so this is a step in that direction. Yeah. Okay, so now I have some more labs, but now I want to go into more on these operators that you were mentioning on the so here. So let me go. So let me show the idea. I just want to give you some intuition. So this is a lab, and supposedly people are supposed to do exercises, but maybe I just show things. And if you have questions, we can go things. So I want to show you some of these operators. So you've seen here uniform and convolution. Let me show probabilistic choice here. an example with probabilistic choice. Okay. So, and then I'll explain what's going on. So here I have a uniform from 1 to 10 and a uniform 5 to 6. So that means there's some chance, and I combine them using a choice. So there's 90% chance that I'm just going to go from 1 to 10, but 10% chance I'm going to be between 5 and 6. So you can see what happens. There's kind of a kink here. In the middle, it's going up higher because there's more chance that it's between 5 and 6. And I can actually give this a bigger value immediately. So if you look at here, for example, you can see there's a kink. Yeah? So this is the probabilistic choice. Sure. Any value you want. So here, the edges are very low, but the kink is huge now. So you're most of the time between 5 and 6, but sometimes outside. And then you can combine things. For example, maybe this one is combined like this. Then, but maybe I'll give a bigger one so you can see better. So you can see the kind of thing that's going on. Let me put a 9 here. No, I have to execute it first. So here, for example, you can see there's still a kink between 5 and 6, but the other one is now much smoother. It's a convolution.
So this gives you some idea of you find interesting situations where the choices don't overlap big time. Right? There's a different kink. Now it's flat. Like that, right? There's a really nice one which we show later. You might you would say, well, imagine I have two things. I'm going to be first to finish. Right? I got things I'll do twice first. How much do I gain in time?
Okay, let me show that one. Yeah, that's a good one.
Does that give you intuition? Right? You can actually see how much do I gain for that for doing 2 in power, 3 in power. And you actually see, it's a law of diminishing returns, as you can expect. We're quantifying that diminishing return. Right? Or last efficiency conversation.
We do, but it's not built into the tool.
We do actually have a calculation like that. Like if you describe the whole language and then say, I'm going to render it this way.
So here, for example, so if you look here, so this is Neil's example. So you have the blue one is just uniform from 1 to 2. But the green one is you have 2 of those guys, and you're waiting for the first one. First to finish between 2 uniforms. And clearly one of them is going to come a little earlier than the other one. You can see it here. At 60%, for example, you're going to hit the green one before you hit the blue one. So you get some extra, it's quicker. So if you want to do something, if something has variation in time, if you do it twice, if the variations are independent, then one of them is going to come quicker. But I can show also 3.
So one of the interesting things here is the uncertainty that you capture with your change between design uncertainty and operation uncertainty. Right? When you have design uncertainties, they get grounded out into a design decision. So you can represent both design uncertainty and operational uncertainty at different stages of design. The philosophy of this goes on in this way. It's like because you can go to engineers and say, how long will this take? I don't know. Could you give me a loan and I go back? Oh, this less than it's going to take more of this, I'm sure. That's a design uncertainty. You can then see if that
It's just an uncertainty, and you can also represent it using a delta.
Yeah, and the question you then ask is, how critical is the level of uncertainty for me to make nuts? Do I need to refine this uncertainty by doing this work? Or can I leave that till later if I persuade myself? Because the thing that you find most people do in systems is the difference at the end. That's what they all think, right? This way you do see the difference, where the difference is going to be.
It is a difficult thing to the end, and they optimize doing that.
Yeah. Yes, that's common, isn't it? To optimize something that's actually not actually upper
here's another example. When I have two, you see, the green one is when I have two parallel tasks, I'm waiting for the first. So you can see there's a gain. The gap between the green and the blue is kind of big. But if now I have add a third one, I get even more gain, but it's less. There's like diminishing returns now.
This is assuming they're all independent.
They're all independent, yeah. You're assuming you're all dependent.
And if we change that to a last to finish operator, is that easier?
Oh yeah. Well, yeah, sure. well, you
Right, this is the point. You can ask those questions. And then you can say, how dependent is it actually on the CPF?
Yeah.
It turns out this is sort of generic.
So here's with the last to finish.
This is something that you can dig out.
So last to finish is this notion of a straggler. You wait for all of them to finish now. You have to wait for all of them.
And this is why if you do have like a hidden tag.
Oh, then you get in trouble.
The straggler always.
Oh, yeah.
says-
Stragglers, but then you can actually put a straggler, you can put two stragglers and have them compete and pick the first one and you gain. And this will show you how much you
That's
gain.
exactly
They used to do this in MapReduce environments.
Absolutely.
Correct,
They used
To
track
compute, so they have all this thing of stragglers in MapReduce, but here you can actually quantify exactly how much gain you get. So this is when you have to do all of them. Huh? So this is when you have multiple tasks, so you're waiting for all of them. So the blue is 1. If you have to wait for 2, you have to wait longer. But if you have to wait for 3, you still have to wait longer than that, but only a little bit longer. So that's the opposite of diminishing returns.
Makes sense.
It makes sense, but I can quantify.
But here it's completely quantified, yeah.
And it's really useful to do this when you're talking about in the block fetch algorithm, inside this system, inside this object system, right? Or the diffusion algorithm. How many, given that I know that I have a number of my peers are connected to this block, how many of them do I ask? Right? We have arguments, one of that they could not reply, and then they slow down. 2 are well eventually. And then so you can now actually model set of behavior, right? Which is and you can model behaviors and you can decision. And then you can say, oh well, if we do this tiny bit at this point, you can cover the 99% percentile. And then you can move on. Because otherwise you spend months trying to work out how to make those types of decisions.
I mean, I presume you have operators that go.
Yes, centiles, yeah.
There's a command in this called centiles.
No.
You give it a list of centiles you're interested in, and it returns you the list of
Yes,
time.
we once came up with something called performance. Specifying including response time distribution.
So the centiles, bearing in mind this whole lot of half. The centiles operator is allowed to return you bad enough. Because the CDF is improper.
Yes.
So if I ask for the 95th percentile,
And
only
it
gets
doesn't
90%.
actually exist.
right?
Yes, yes,
The,
right.
the time at which that occurs
Right.
is nothing.
Yes, yes.
Actually, it says never. It says never.
Yeah.
In user interface.
The user
In the
interface
world
is
of
like that.
negative time.
So you can do plot. Actually, just do what the CDFs. I was building that's the sort of it's even the plot. And you can also plot with negative inverse. Because sometimes you're interested in tail, so you're interested in
Yes,
probability, right? And the good thing is this does it because it's just a reference, right? Very difficult.
Can you plug real-time streaming data?
Well, as I said, you can construct a distribution.
Yeah.
Right, that's completely empirical. I've just measured points.
Yeah, yeah,
Right,
sure.
it's a histogram. I put them in place, and then turn that into a linear interpolation between the buttons.
And actually, we have a whole model around that. Some geography, some sort of packets, some speed, some everything else. Do that with the time. Where we're delivering that delta, you're the last 10 seconds. Right? So, yeah, yes, the answer is we can build this into monitoring and service assurance.
Here's another example where I compare the green, so the blue one is a uniform from 1 and 2. The green one is at least 1, which is the first to finish. The yellow one is at least 3, which is all to finish. But I added a red one, which is at least 2. So you can see at least 2, when you have 3 things, is not the same as a uniform, okay? It has this interesting intermediate curve, huh? So if you look at the formula for F, that's the formula for at least 2, okay? So at least 2, there's 3 ways you can get 2. You can get AB or AC or BC, okay? So you have at least 1, at least 2, at least 3.
So we just want voting systems. Voting systems is simply critical systems.
So it's interesting where at least 2 is not quite the same as uniform, even though it's like halfway.
You think it would be worse than you think it would be worse than what? It is at one edge. It doesn't move the. I don't know if it moves the mean or not.
See, the thing about at least 2 compared to the others is that it actually it's flat in the beginning and flat at the end, where the uniform has a kink.
Could you plot the PDFs of that?
Ah, okay, sure. It's easy.
Before you do that,
This is the lab session.
This is the lab session, and I take requests.
We're still recording.
Yes.
that's
Fine.
fine.
I think this is fine because we're not. There's reasons to not record. We're just not going to see. That's good.
Right, so you mentioned
Right.
the performance trees. Yeah, I tend to think that I took a look at them at one point, and I think that they didn't have a way of speaking about both failure and delay. You could only do one of them, but not two of them.
Delay.
Right. Yeah. And then so I think that one of the key contributions of ΔQSD is that ΔQ incorporates delay and failure in just one item. And so you have access to both of those elements in just one entity. And you can reason about them. But there are tools out, I've seen some, it's not my profession, but I've seen some which can do one, but are completely unaware of the other.
Failure loads effects analysis.
Yes, for example. Yeah.
So you need both. But okay, I mean, I think that's not to. It turns out that I think this notion of quality of attenuation is probably the
Fundamentally, quality attenuation is whatever is the deviation from your ideal and perfect response. So, what you would really like is things that never fail and respond instantaneously, right? You can't have those.
Yeah.
So the question is,
Perfection.
Yes.
it's in the model as the top of the partial order. So the question you need to ask is how far away am I from the perfect response, and how far away do I need?
Changes the mindset. There's actually now, if you get people to think this way, they accept non-success.
Oh, it's a tall order. I mean, not very many people are changing their mindset.
Because that makes systems feasible. Even the 999 calls in this country have 1 in 500 chance of it. Yes, that's what the spec is. Right? What?
You wouldn't want to
One
be
in
that
every
person.
500 people has an emergency is left hanging.
Well, they failed to make.
Yeah.
But they can try again, huh?
I have to try again.
It's supposed to be a one. It's supposed to be a one. This is what it says. Right. 1 in 500. It's supposed to be a balloon choice.
Yeah.
But if you try again, it will not be independent.
It's like, but that's how it's spec. It doesn't have to be perfect. Okay. Right. Normal telephone calls. Maybe it's only 1 in 200. That's it. The spec is 1 in 200. They deliver 1 in 500. normal telephone calls are wavelength.
So you just try again if it doesn't work.
Yes, right. But I'm just saying that's the way the real world works.
So humans, they love to retry. Retry is always.
This actually,
Especially as the software people.
this is absolutely. We took that last and first to tutor finish. Look what we ended up with.
Yeah, it's nice.
Yeah, I was
The PDFs are interesting. They're very different, huh?
yeah,
They're completely, yeah.
that tells the difference between first, last, and finish and the voting.
So first to finish, there's a lot of chance you're in the middle. Last to finish, you're at the end. And two, while you're in the middle there, huh?
Yeah.
So you're 1, 1.5, 2, huh?
And it shows.
But it's a little bit shifted. It's
yeah,
interesting,
that was
huh?
interesting. It shifted. It's the meaning. The meaning
But
is
it may be more like a geometric mean, okay?
Yes,
1.4, not 1.5, huh?
Yeah.
And the uniform is just a straight thing. So 1, 2, 3. And then you could make more complicated formulas where it's 1 or 2 with 50% chance or something, 1.5, you know? Depends on what you want.
But you can incorporate. If you think about voting systems,
Voting,
say
yeah.
if you put it in systems, you know,
Well, voting, you would need at least 2 here. If you have 3, you need 2 votes, huh?
But in the space shuttle, at 5,
5, yeah.
yes, and basically it had. Let's get this right. In a voting systems, actually you may have had more. It had one voting system by people who were educated on the East Coast, and one voting system by those who were educated on the West Coast. So they chose different schools depending on where you were educated, many different types of that. Right. And then there was another system, the critical one, which there was only one, but it ran a much simpler design. And then they voted between them.
And if the vote was not unanimous, what happened?
Majority.
It's a majority vote.
Ah,
So you
okay,
have to have an odd number of things.
okay.
But they press that all them
That
Well, that's what.
Yeah.
you know what the design failure rate was?
It's pretty good.
No, well, what's
I mean, what did the
what's the design failure rate for planes? 1 in 10 to the 9. 1 in 10 to 2.
you mean that the plane that people die because you can almost always land safely? Is that what you mean?
Yeah, it's hard from space.
Yeah.
From space, it's harder, yeah.
So basically,
Yeah.
when they designed, given that we did actually work with people in one of our things in which we built the space station and the shuttle, we had this discussion. So we got these numbers out, as these are ballpark figures. So they were designed to failure. Right? Well, they were
These
designed.
are the good clients that have access or can work out the specs.
This is okay. So this was the. I'm not saying anything about who these people are. But there was the interesting clash was between the system engineers, these are the kind of people who did work on the station, who had this mentality about failure is a possibility, right? And we have to work on it, and we have various ways to mitigate all that kind of stuff. And the people coming from the data networking background,
Yes.
who took basically everything would get the best effort, and it would be what it is.
There was
no a
priori numbers.
And there were neither a priori
We just
nor
do the best. Just best effort.
Right? It's just best effort, right? You will get what you get, right? And we will make it as best as it can be, but whatever it is, that's what you get, and we're not going to try and work out what it is. We're not going to, it'll just be what it is.
I'll tell you the look of some. I'm not going to get that because it's either way. I will tell you afterwards. Consequences of that. And then when we get one of the consequences was when I count. Actually, one of the things that I share. Oh, wow. Basically, what what was particularly interesting here is they couldn't admit that they couldn't understand. Like their whole mental depth when they're going. So we're not just dealing with how they actually how they work. We're actually dealing with people's sense of self that gets embodied in these things. And basically when you attack people's sense of self, they attack back. They attack back, right? And it's, you know, you think, oh, this is just pretty close. Right? This is
Much
this
more
is existential. This is
Yeah.
was that we finished?
Yeah, we're kind of,
Do you want to pause before?
we can pause the recording. Yeah.
So